Hello everyone. In this video I would be going through the Flipkart project. So this is the GitHub link for the project. This project aims to analyze customer support data to identify the major factors influencing customer satisfaction scores and to develop predictive models that can classify these scores accurately. The goal is to provide actionable insights that can help improve customer service strategies and enhance overall customer experience. So first, these are the important libraries which were to be imported. Dataset was loaded. So here are the first 5 rows of the dataset. To get the number of columns and number of rows in the dataset, shape function is used. So this is the basic information of the dataset, like whichever columns are there, what are their data type, etc. To get the number of duplicate values in the dataset, this was the syntax. Similarly, for getting the missing values or null values, here we can see customer ranks, order ID, order date, time, customer city, product category, item price, connected handling time. These variables have missing values. So this is a heat map for visualizing the missing values. So the dataset contains 85,907 records and 20 columns covering various aspects of customer support interaction. It includes categorical variables such as communication channel, query category, subcategory, agent details, and manager information. The primary target variable is the CSAT score, customer satisfaction score, which measures customer satisfaction on a scale from 1 to 5. Additionally, the dataset has identifiers, timestamps, and numerical variables like item price and handling time. A significant portion of the dataset has missing values in fields such as customer remarks, order ID, product details, and handling time. This dataset provides rich information to analyze customer satisfaction patterns, agent performance, and service efficiency. Now in this section, first we are getting the column names of the data. These are all the column names. Then this is the basic statistical summary for the data. So these are all variables in the dataset, and which variable is describing what is written here, like unique ID, unique identifier for each customer support case, subcategory, specific subcategory of the issue under the main category. Like this, every variable is describing something. So now we are checking unique values in every column. So here you can see each column has specific unique values, which is depicted here. Next section is for data wrangling. So in this project, extensive data wrangling and analysis were performed to clean and prepare the customer support data for modeling. Initially, columns with excessive missing values, more than 20% missing data, were dropped to focus only on useful variables, which resulted in the removal of columns like connected, handling time, and customer city. The remaining missing values were then handled by filling categorical columns with their most frequent value mode and numerical columns with their median value. Next, only the most relevant features such as channel name, category, subcategory, tenure bucket, agent shift, and target variable CSAT score were selected for analysis. Categorical variables were encoded using one-hot encoding to prepare them for machine learning models. During the exploratory data analysis, it was observed that dataset had a strong imbalance in the target variable with the highest CSAT score of 5, dominating the records over 59,000 entries, making it a highly skewed dataset. So next section is for data visualization. The first chart is is the distribution of customer satisfaction scores. So this is the chart. This is a count plot which was chosen because it clearly shows the frequency of each CSAT score. Since CSAT score is categorical variable, this chart helps quickly identify the most common scores and highlights the imbalance in the dataset. The chart shows the most customer gave the highest CSAT score of 5, indicating high overall customer satisfaction. Next chart is the next chart effectively shows the distribution of categories within a variable. It clearly highlights which categories are most frequent and helps understand the comparison of data set. The chart shows the most customer interactions occurred through a particular channel, indicating a strong customer preference for that communication method. So are there any insights that led to negative growth? Yes, this insight helps the business focus resources on the most popular customer channels to improve service and efficiency. However, ignoring less frequent channels may lead to negative growth if those customers feel undeserved, possibly reducing satisfaction among smaller customer segments. So the next is a box plot which depicts the customer satisfaction scores versus the channel name. So this chart shows which categories or channels have higher or lower median customer satisfaction scores. Talking about any insights for the negative growth. These insights help business identify which channels or categories are driving customer satisfaction and which need improvement. Ignoring categories with lower scores may lead to negative customer experiences and potential loss of customers from these segments. Next chart is a violin plot. The violin plot is chosen here because it shows both the distribution and density of scores across different tenure buckets. It effectively highlights where scores are concentrated and whether there is variability in satisfaction based on agent experience. Talking about the negative insights for the negative growth. So if ignoring insights may lead to negative growth if inexperienced agents consistently deliver poor customer experiences. Next chart is a box plot for scores by agent shift. So here box plot is chosen because it effectively shows the distribution of scores across different agent shifts. This chart reveals the scores vary across agent shift, highlighting whether certain shifts are associated with higher or lower customer satisfaction. Talking about the negative growth. So this insight can help optimize staffing by identifying shifts that need improvement or additional support. Ignoring shifts with low satisfaction may lead to negative growth due to poor customer experiences during the periods. Next chart is also a box plot which is for outlier check. This chart is identifying outliers in numeric columns like item price and connected handling time. It shows where extreme value exists, indicating potential data errors or unusual cases. Talking about the negative growth. Yes, detecting and handling outliers can improve the accuracy of analysis and models, leading to better business decisions. Ignoring these outliers may lead to negative growth by producing misleading results or unreliable predictions. Next chart is the correlation heat map. So this is the correlation heat map. So the heat map is chosen because it effectively visualizes the correlation between multiple numeric variables. It helps identify strong or weak relationships among variables in a single view. This chart shows weak correlations between most variables and scores, indicating that none of the features have a strong linear relationship with customer satisfaction. The next column is for feature engineering and data preprocessing. Here, first we are handling the missing values. So here the techniques used for missing values are dropping columns with accessing missing values. Columns with more than 20% missing data were dropped. These columns had too much missing data, making them unreliable and difficult to impute accurately. Mode imputation. Mode is the most frequent category and works well for categorical variable to fill missing values while preserving common trends in the data. Median imputation. Median is robust to outliers and prevents skewing the data, making it a safe choice for numeric columns with missing values. Next, we are handling the outliers. This is the plot for checking the outliers. So here the outlier detection is done by box plots. Box plot is used to visually detect outliers in numeric variables like item price and connected handling time. So here I have done indirect outlier treatment through median imputation. While filling missing numerical values, I used the median instead of mean. Median imputation minimizes the influence of extreme outliers because it is not affected by high or low extreme values, making it a robust method for missing value treatment. Next, we are encoding categorical variables. So here I have done one hot encoding. The one hot encoding handles nominal data effectively. One hot encoding is suitable for categorical variables with no natural order, like channel name, category, subcategory. It prevents ordinal assumptions. It unlike label encoding, one-hot encoding does not impose any order or ranking among categories, which makes it safe for non-ordinal variables. Model compatibility. Many machine learning models like random forest, logistic regression, XGBoost require numeric input, and one-hot encoding works well with them. One-hot encoding avoids dummy variable. By using drop first true, this project prevented multicollinearity issues by dropping one dummy column per feature. So next is feature manipulation and selection. So for feature manipulation also one-hot encoding was done. Feature selection was done by random forest classifier. So here are the top features. So most top feature affecting the customer's satisfaction is channel name inbound. The random forest feature importance was used as a primary method for feature selection. This model-based approach ranks features based on how effectively they reduce impurity when making splits in decision trees. It provides a straightforward way to identify which variables have the most influence on predicting their scores. So the feature importance analysis revealed that the most influential factors affecting the score include the communication channel, agent tenure, and shift timing. Features like channel name inbound, channel name outcall had the highest importance as scores, suggesting that the mode of the interaction significantly impacts customer satisfaction. Additionally, agent experience represented by tenure bucket greater than 90, 31 to 60, and on job training emerged as critical predictors, indicating that more experienced agents tend to deliver better service. Shifts timing such as evening, morning, and night also played a key role, possibly reflecting variations in workload, agent performance, or customer expectation across different times of the day. Furthermore, issue types like subcategory return request showed relevance, like due to emotional or complex nature of such queries. Overall, the model highlights that both operational factors and issue characteristics are key drivers of customer satisfaction. So next is data transformation. So the data transformation was necessary in this analysis to prepare the dataset for machine learning models. Since the dataset contained several categorical variables such as channel name, subcategory, tenure bucket, and agent shift, I applied one-hot encoding to convert these categories into numerical format. This transformation was essential because machine learning algorithms like random forest require numeric input and cannot process textual or categorical data directly. Next was data scaling. So the method used to scale the data was standard scaler from the scikit-learn library. Standard scaler standardizes the numeric features by removing the mean and scaling them to unit variance. This method was chosen because it ensures that all numeric variables have the same scale, preventing features with larger numeric ranges from dominating the model. Standard scaler works well for models sensitive to feature magnitude such as logistic regression, where differences in feature scales can affect model performance. Although scaling is not necessary for tree-based models like random forest and XGBoost, it can help improve the performance and convergence speed of models that rely on distance or gradient optimization. Next is dimensionality reduction. So dimensionality reduction is not critically needed for this dataset at the current stage. The number of features used after feature selection and encoding is relatively small and manageable, which reduces the risk of overfitting due to high dimensionality. Additionally, the model applied, such as a random forest and exhibits in further machine learning models, handle high dimensional data well and are not sensitive to the number of features. However, if more features are introduced in the future or if more complex encoding methods generate a larger feature set, dimension reduction method like PCA could be considered. Next is the data splitting. Here we are splitting the data into training set and testing set, which is 80% training set and 20% testing set. So I use the test split ratio of 80-20. Why 80-20? Balance between training and evaluation. Using 80% data for training allows the model to learn well from a substantial portion of data. The remaining 20% is kept unseen during the training for an unbiased evaluation of the model's performance. Common industry practice is 80-20. It is widely accepted standard for splitting datasets in machine learning tasks. This is important to avoid bias if some classes are underrepresented. So next we are handling the imbalanced dataset. So the dataset is surely imbalanced, particularly with respect to the target variable. A significant majority of the responses, nearly 70%, have a score of 5, while the remaining scores 1 to 4 are disproportionately underrepresented. For instance, scores 2 and 3 make up only around 1.5% and 3% of the data, respectively. This uneven distribution indicates a class imbalance, which can adversely affect model performance by making it biased towards the majority class. As a result, the model may achieve high overall accuracy but perform poorly in correctly predicting the minority classes, which is evident from the low precision and recall for the scores. So, to address the class imbalance in the scores variables, I used SMOTE, synthetic minority oversampling technique. The dataset was highly imbalanced with scores 5 accounting for nearly 70% responses, while 2 and 3 were significantly underrepresented. This imbalance could lead to biased models that perform well only on the majority class and fail to capture patterns for minority classes. SMOTE helps by generating synthetic samples for the minority classes rather than duplicating existing data, which improves the diversity and balance of the training set. This technique was applied only on the training data to prevent data leakage. As a result, the model becomes more capable of learning from all classes and making fairer predictions across the full range of customer satisfaction. Next section is the machine learning model implementation. So the first model implemented here is random forest. So this is the classification report for the random forest model. This is the confusion matrix. These are the predicted values and actual values. So in the next step, so like in this model, we achieved the accuracy score of 0.69. Now we are implementing hyperparameter tuning to increase the accuracy of the model. After hyperparameter tuning, the model accuracy increased to 0.69. So here I used grid search CV as the hyperparameter optimization technique for tuning the random forest classifier. Grid search CV works by exhaustively searching through a manually specified subset of hyperparameter space and evaluating each possible combination using cross-validation. This technique was chosen because it is straightforward, reliable, and well suited for datasets of moderate size and dimensionality like the one used in this project. It ensures that all specified parameter combinations are evaluated, which increases the likelihood of finding the best performing model configuration. Although it can be computationally intensive, it provides a more comprehensive optimization compared to methods like random search CV, which samples a limited number of combinations. In this case, grid search CV helped fine-tune parameters like the number of trees, maximum depth, and split criteria, ultimately improving the model's predictive performance without altering the data distribution. Yes, after applying grid search CV to optimize the hyperparameters of the random forest classifier, there was a noticeable improvement in the model's performance, especially in terms of overall accuracy and class-wise F1 scores. So the accuracy in the model was 69.11, heavily biased towards CSAT scores. After applying grid search CV, the model accuracy improved to 69.3%. Better class-wise distribution of predictions, slight but meaningful improvements in F1 score and recall for minority classes. So the next model used here is logistic regression. So this is a classification report for logistic regression, and here we achieved the accuracy of 0.69, i.e. 69.3%. So this is the confusion matrix. In next step, we applied hyperparameter tuning by grid search CV only. After applying hyperparameter tuning, we achieved the accuracy of 69.39%. After applying grid search CV to the logistic regression model, there was a modest but measurable improvement in performance over the baseline default logistic regression model. The improvement was primarily observed in accuracy and F1 scores for some of the minority classes, though class imbalance still posed challenges. Accuracy increased slightly, for example, from 69.38% to around 69.39%, depending on the best parameter combination selected. Precision and recall for scores 1 and 4 showed minor gains, indicating the model became slightly better at detecting low satisfaction levels. F1 score improved in a more balanced way across multiple classes, especially for mid-range satisfaction like 3 and 4, which were previously underperforming. So the next model used here is XGBoost. After applying XGBoost, we got the accuracy of 69.27%. This is a confusion matrix for XGBoost model. Next is the we perform hyperparameter tuning for improving the accuracy and all the other scores. After applying this, we got the accuracy of 69.39%. So the observed improvement accuracy increased slightly from 69.2% to around 69.3%, depending on the best parameter combined selected. Precision and recall for SCSAT scores 1 and 4 showed minor gains, indicating model became slightly better at detecting low satisfaction levels. F1 also improved in a balanced way. So which evaluation metrics did I consider for a positive business impact and why? For a positive business impact, I focus on precision, recall, F1 score and accuracy. While accuracy gives us an overall performance view, recall helps identify dissatisfied customers who might churn, and precision ensures we act only on genuinely unhappy customers. The F1 score balances both, making it ideal for handling class imbalance. Together, these matrices ensure the model support effective customer recovery and boost retention. So the random forest classifier was selected as a final model for predicting customer satisfaction score due to its strong overall performance, robustness to imbalance data, and ability to provide meaningful insights through feature importance analysis. During model evaluation, random forest outperformed both logistic regression and XGBoost in terms of accuracy, precision, recall, and F1 score. Especially after applying SMOTE to address the class imbalance issue in the training data, it showed a better balance between sensitivity to minority classes and overall prediction accuracy, which is crucial in a multi-class classification task like this customer satisfaction prediction. In addition to performance, random forest flexibility in handling both categorical after one-hot encoding and numerical features made it highly suitable for this dataset. Unlike logistic regression, it does not assume linear relationship between variables, and unlike XGBoost, it required less hyperparameter tuning to achieve optimum results. A key advantage of random forest is its ability to generate feature important scores, which helped identify critical factors affecting customer satisfaction such as channel name, tenure bucket, agent shift, and certain subcategories. Furthermore, random forest is relatively easy to implement, robust to overfitting due to its ensemble nature, and well suited for deployment in real-time decision system. Considering all these aspects, high accuracy, ability to generalize well, ease of use and interpretability, random forest was the most effective and practical choice for this final customer satisfaction prediction model. So the final model used for this project is random forest classifier, an ensemble-based supervised machine learning algorithm that builds multiple decision trees and combines their prediction to improve accuracy and control overfitting. Each tree is trained on a random subset of data and uses a random subset of features for splitting at each node, ensuring diversity among trees. During prediction, the model aggregates the output from all individual trees using majority voting for classification, which improves overall stability and reduces variance. One of the key strengths of random forest is the ability to calculate features importance that I told already. So random forest improvement tool reveals several key insights. Channel name inbound and channel name outcall were among the most important features, indicating that in method of customer interaction, it significantly influences class satisfaction. Agent-related attributes such as tenure bucket, on-job training, and agent shift evening also ranked highly, suggesting the experience level and shift timing impact several service quality. Certain issues type like subcategory return requests also appeared as important, pointing to sensitive customer concerns. These insights were visualized using a bar plot of top 10 features and ranked by importance, helping stakeholders identify operational areas that affect customer satisfaction. So for future work, the best performing model is saved in a pickle file. So predicting the scores for unseen data is 5 only. So coming to the end of this video, for the conclusion, this project focused on building a robust machine learning model to predict the customer satisfaction score based on operational and behavioral data from customer support interaction. The ultimate objective was to uncover key patterns that influence customer satisfaction and help business make data-driven decisions to enhance service quality. So the exploratory data analysis phase revealed an extreme imbalance in the scores, with the majority of customers rating their experience as a perfect 5. This imbalance presented a major modeling challenge, as most classifiers naturally gravitate towards predicting the majority class. To resolve this, synthetic minority oversampling technique was applied, which synthetically increased instances of minority class in the training set, ensuring the model could learn patterns across all levels of customer satisfaction. Feature selection was performed using random forest feature importance, which ranked variable based on the contribution to model performance. Key drivers of the model included, which I told already. After balancing the data, multiple classification models were tested, including random forest, logistic regression, and XGBoost. Among these, random forest yielded the best accuracy and robustness, benefiting from its ability to handle both categorical and continuous data. Though highest accuracy was with XGBoost, but rest classification scores like precision, recall, and difference scores were higher in case of random forest. To ensure generalization, train transfer was implemented with stratification and hyperparameter tuning using grid search CV could be explored to further optimize model performance. Additionally, advanced assemble techniques and deep learning models may offer better results if more training data becomes available. Thank you.